Pleasure for me to talk today about the MSC Nastran 2014.1 release along with the Patran 2014.1 release. And I hope that all of you noticed that the release was formally done last week. You should have gotten invitations to go to the download site or have your administrators go to the download site to get the latest version of the code. Before I really talk about 2014.1, I'm going to do a quick review of MSC Nastran 2014. 2014 was really a major release for the Nastran product. We effectively had new capabilities or improved capabilities really having to do with all the different themes associated with MSC Nastran. That is, we did work in HPC performance, which I'm going to talk about in a little bit more detail, linear analysis, some improvements to activating and deactivating RBEs, and some improvements in the subseq command, which really makes it much easier to deal with large number of load cases. We have improvements in dynamics and acoustics, particularly having to do with combination of rotor dynamics and super elements, but also improvements associated with poroelastic materials, some additions to OpenFSI to allow rotations and moments to be dealt with, and some enhancements to monitor points. The 2014 release was also saw major new capabilities having to do with Nastran embedded fatigue. Of course, Nastran embedded fatigue is really a new capability that's really been evolving since the 2013 release, and the 2014 release introduced the capability of dealing with weld modeling and getting the life associated with, or the durability associated with welds. And then in nonlinear analysis for solution sequence 400, enhancements to linear perturbation, and also the use of linear perturbation on nonlinear preloaded systems. Really, the objective in life is really for Sol 400 to have all the capabilities associated with the linear solution sequences as well, or at least the most common ones, and some enhancements to segment contact. And finally, there was a capability to do optimization based upon a design of loads. So I can't talk about all those, but I'll just quickly go through high-performance computing, because that's also a theme for the 2014.1 release and 2016 as well. So, of course, frequency response is the heart and soul of MSC Nastran, and some work has been done to allow FastFR to be used with non-symmetric systems as well. The particular application was a problem that was predominantly symmetric, but there were some non-symmetric DMIGs that were put into the system. And you can see that now between previous 2013.1 and 2014, we got quite a dramatic improvement in terms of the performance of the code. That was also true for using weakly coupled acoustic analysis. This would have been for interior coupled analysis. And you could see using the Krylov solver typically about a 40% improvement in performance for a reasonably large model. When acoustics was used for exterior cases in Sol 108, the performance was even greater, more dramatic in terms of the reduction of computational time. In fact, depending on how many CPUs you had, the factor was over a factor of 20. So one of the big things that happened in Sol 400 in the 2014 release is we introduced a new parallel solver, and that's important because the performance was so good and so promising, it really is things that we're going to take over into the future. So in the case of shell-type models that really don't have particularly large bandwidth, one could see that actually it was a little slower in serial mode, but much more importantly, when you had multiple cores in your system, the solver time dramatically reduced. And dramatically reduced was less solver time than the traditional MSC LDL solver. And if you looked at the total computational time, you'd say, well, that wasn't particularly dramatic. But if you had models which involved effectively solver-dominated jobs, such as this 15 million degrees of freedom job with large bandwidth, you could basically see that effectively the solver time actually did good reduction in wall time all the way up to 30 cores, and the total solution time, because it was solver dominant, also had a dramatic reduction in computational time. And I should say these times associated with Sol 400, they will improve again in actually the 2016 release. So let's talk about Nastran 2014.1. Nastran 2014.1 is a point release. There are really two things in terms of new capabilities, and of course the other one, which we never really mentioned, is there were significant amount of defects that were closed between the 2014 release and the 2014.1. So the two topics I'm really going to talk about is the use of the iterative solver, the CASI iterative solver for parallelization, and some new capabilities for weight optimization. So the CASI solver that's an MSC Nastran, traditionally it's used for, again, large, bulky models. Models that are solid, hex elements, TED elements, penta elements, with generally speaking large bandwidth. And what's been done for the 2014.1 release is the solver's been replaced, it's been updated, it's going to give better performance in serial mode, but more significantly, it's also going to give better performance in parallel mode. So the way iterative solvers work, don't expect this to go parallel up to 30 cores, but in terms of the sweet spot, 4 to 8 cores, you'll get very good performance. If you do really huge models, you'll be able to take it out in terms of more cores than that. So these are effectively what we're seeing in terms of CASI time associated with such a model and what it did in terms of the total time of the system. If you actually compare this to the MSC LDL solver, which is a direct solver, you can see that even serial or multi-core, massive improvements over the traditional Nastran solver, direct solver. Now let's take a look at a bunch of problems, because this is kind of gives some interesting data. One is basically the value of the 2014, I should have said 2014, not 2014.1, and the blue is really what we're getting in 2014 on serial. So with the exception of this one problem, even on serial, things are improved. And then when we add multi-cores, we get, again, an additional reduction. The interesting thing to see on this is that the performance is not only based upon the size of the model. So these jobs were between 2.2 and 8.8 million degrees of freedom. but they also depend upon the number of iterations you take. So we get more parallelization if we have, in fact, more iterations in the CASI iterative solver. So what this really means is that there were problems before that you might have said, well, it's a poorly conditioned system. I don't want to use the iterative solver because I know it will run slower. But now, because of the parallelization, utilizing the iterative solver will be effective even on moderately ill-conditioned systems. And what's the additional benefit of the iterative solver? Of course, the iterative solver requires a lot less memory. Now, of course, you always need to caution, you cannot use Langcho's eigenvalue extraction. You cannot use ACMS in conjunction with iterative solvers. But if you have large SOL 101 problems or large SOL 400 problems, it's a very effective tool in your system. So what do you need to do to use the iterative solver? First of all, there's a bulk data card called ITER, and you activate the CASI preconditioner, and you give the convergence associated with the iterative solver. I tend to use e to the -6, and then you specify SMP on your command line. From a licensing perspective, there are no changes to the CASI license when you're running in serial mode. But in 2014.1 version of MSC Nastran, you will need an additional feature line in your license file. And there is an interim license file that's on the software download site that can be used to pick up this license. If you want to use the iterative solver with SMP parallelization, then basically when you say SMP equals something on your command line, it will basically utilize the SMP licensing feature. Move on to optimization. Optimization has one particular feature. It's actually an extremely useful feature and perhaps something we should have done before. But it allows you to treat weight as a response to optimize, but the weight is not the total weight of the vehicle, but the weight can be tied to a particular property ID or material ID. So you could have one response function having to do with the weight of the aluminum, another response function having to do with the weight of the steel, and it gives you better insight in what you should do in terms of your design, and it gives you insight in whether or not I should do trade-offs in the design. In other words, should I replace my metallic part with a composite part? Should I replace my low-strength steel with a high-strength steel in the simulation? And we'll get to that a little bit in a second here. So what's the objective is it basically tells you on a part-by-part or property-by-property basis or a material ID by a material ID basis, and is a very useful thing, especially when you're talking about an OEM or somebody who's dealing with large assemblies with many properties and many material IDs. It actually built upon something that existed in the program before, but not too many people knew about it, which was when you did optimization before and you used the parameter P2 equals 16, or you included 16 in the calculation of P2 on the dopt-param bulk data file. We used to tell you this information. We used to tell you what was the material weight based upon the material ID. Now we're actually using that in a response function. So one example that we have is this example of the shop tower. You might remember the shock tower from the 2014 presentation. There we used the same model to demonstrate Nastran embedded fatigue for weld connections. So now we're going to do the same thing as we did before, but what we're going to do is we're also going to consider the the response function to be the weight based upon the property ID. And in fact, for this particular shock tower, one would observe that we had really 15 different property IDs of different thicknesses. And as opposed to what we did before, when we attempted to do the optimization, we're going to do the same thing, but we're going to have a little bit greater control. And we managed to reduce the weight by 24% in this analysis. And we managed to do this by also achieving an increase in the design life by 14%. So that's a good thing. And of course, before we used Nastran embedded fatigue, you might have done an optimization problem, but you weren't able to include fatigue constraints or fatigue in the analysis, and now you can do that as well with MSC Nastran. So it's an easy input to do. It's basically your DRESP1 option, and we basically have a response type that's called WMPID, and depending on which options that you use on the DRESP1, it will either be based upon a material ID or a property ID. So we did this option, and I guess some of us said, well, that wasn't quite enough. What you're really interested in doing is optimization based upon cost. So if you really wanted to make that trade-off study between what should I be using, aluminum or steel, or different types of metallics versus composites, you would want to be able to associate a cost associated with the given mass. And that's really quite easy to do. We would have set up our two DRESP1s for our aluminum and for our steel, and they would have had, you know, material IDs 102 and 202, and they would have been called 24 and 25. And then one would have constructed a new response function, which is called from using DRESP2, and it's going to have the name of cost, and it's going to have an ID of 50, and the 60 is going to refer to a particular equation. And then we're going to give a couple of constants that are going to be used in the equation. We would effectively give the cost per unit mass of the aluminum and the cost of unit mass for the steel, and we would have defined our equation as the product of the cost versus the calculated value of from DRESP1 and DRESP2, and then we would have done the optimization based upon cost, which is certainly what we want to do as engineering management wants to do. Okay, let me move on to Patran 2014.1, and I'll just walk through this, and then Alan Casario is going to do a little demonstration. So the Patran 2014.1 release really has three major capabilities, and of course as well it has defect corrections in a variety of areas. The first one, which is really what the demonstration is going to be about, has to do with the SOL 400 preference, and we'll get to that in details. Then the other one, which really isn't a new command or anything for you, but the direct results access, or the so-called DRA, has been substantially improved so that a few of the data blocks were missing, and we can do a better job when we are in mode equals I8 for MSC Nastran. And I'll use this opportunity to say that in the future, mode equals I4 will no longer be supported by MSC Nastran. Finally, we have a capability that's called brake pad, which is what happens if Patran does terminate on you. It allows you to make our life easier in tracing back the issues. So the big thing is the new preference. So we have a structures preference in Patran. That preference remains. But that preference for nonlinear analysis, it had some SOL 106 stuff, 129, 159, 600, 700, 400. It was very confusing to the users. So now we're going to have one dedicated preference associated with SOL 400, which is going to be the implicit nonlinear preference. So I'm not going to race through all the different features. I can say that what we've done on the first round, and there will be a second round, is that we have supported the most important ones and the most important materials and the most important elements, and make sure it was absolutely bulletproof until we go to the next one. There are some features that are not supported, some of the more advanced materials, the cohesive elements and things associated with fracture analysis, and some of the heat transfer analysis has not been supported. So this is going to support SOL 400, mechanical analysis, heat transfer analysis, and certain loosely coupled analysis where we're effectively doing a heat transfer analysis followed by a structural analysis. There are some things, again, in the area of contact and user subroutines and perturbation analysis that are not supported, but we're doing our best to make a complete release. So a large portion of this, as I mentioned, is to reduce the complexity associated with the analysis. So when you start off Patran, you'll see effectively when you go to your preferences, the default is still going to be structural analysis, but there's this new preference called implicit nonlinear, and it will be a bit possible for you to take all your data, your stuff that's in your current Patran databases that's in a structural preference, and by switching on implicit nonlinear, you're not going to lose the data. The data will be moved into your implicit nonlinear preference. One of the things that's getting organized for doing really coupled analysis is rather than having one menu talk about structural material properties and another menu to talk about thermal material properties, these menus have been combined. One of the objectives is to reduce the amount of hand-mouse motion, and so you don't have to go up and then go back down. Things are being grouped to a more consistent manner to improve the look and feel. Same was absolutely done associated with contact analysis, and I think we'll see that in the demonstration, that again, by removing some of the things that weren't relevant associated with SOL 600 and associated with SOL 700, we've been able to reorganize things. So clearly things having to do with deformable bodies, rigid bodies, or the interaction between the bodies is much more nicely grouped together. Similarly, in controlling load cases, NLSTEP support, again, by removing some of the options that are not relevant for SOL 400, the menus are cleaner, whether or not you're doing static or dynamic or heat transfer or normal modes in buckling. And probably the most useful, or one of the most useful features, is combining load cases into subcases. One can basically use model drag and drop type operations in a much nicer way to organize your particular analysis. Finally, let me talk about the termination reporting system. Something came up in this morning's previous presentation. So we're using a tool called BreakPad. It comes from Google, and what it does is if your job would terminate, and I apologize for any terminations of the Patran world, is it will produce a small file, or a smaller file than your standard database file, that contains information that allows our QA team and our development team to figure out what's going on. And so that file would show up in your directory, and we're asking you to send that to MSC Support. Now, one of the things that came up had to do with ITAR. So you should recognize that there can be, and in fact there definitely will be, certain data in this file that could be ITAR restricted. So that's, your responsibility. We are not, with Patran, we are not automatically grabbing this file and automatically sending that to MSC Support. So if you have something that's ITAR, make sure that you're sending it to your local U.S. support guy. Tell them that it's ITAR so that it will be handled more appropriately. So with that, let me transfer, or Srinivas, can you please transfer it over to Ellen so he can run his little demonstration.
Okay, thank you, Ted, and hello, everyone. I am going to give you a brief demonstration of the new implicit nonlinear preference in Patran. So what you see on my screen is a simple model, and when you decide that you want to do a Sol 400 job, the first thing that you're going to do once you've got your geometry and your finite element model set is you're going to go to your preferences menu and pick analysis and set your analysis preference to implicit nonlinear. So right now you see we have about 5 different analysis types in here: structural, thermal, implicit nonlinear, and explicit nonlinear, and aeroelasticity. So most of you must be familiar with the structural preference, which is essentially solutions 101 through 200, excluding the heat transfer ones. So the thermal preference allows you to do solutions 153 and 159 for steady state heat transfer and transient heat transfer. Explicit nonlinear is a dedicated preference for Sol 700, and if you wanted to do a Sol 400 job, you used to have to go under the structural preference and then set your solution sequence to what we called implicit nonlinear, but it was matter of fact, let me just show you that so you understand what I'm talking about. You set this to structural, and you would go to your analysis form, and you would come in here to your solution type, and you would set it to implicit nonlinear. But then you still had the option of running it as a Sol 400 or a Sol 600 job. So if I turn that toggle off, then I would be running a Sol 600 instead of a Sol 400. And all the forms associated with setting up your analysis were confused between Sol 400 and 600. And if you're working in the structural preference, it's still that way. We haven't actually changed anything there. But what we have done is created this new analysis preference called implicit nonlinear, which is dedicated to Sol 400. So when you come in here and you set up your analysis job, now everything is going to be dedicated and specific only to Sol 400. And that includes setting up the whole entire job, from materials to properties to loads and boundary conditions, MPCs, contact, and analysis parameters. So I'm just going to kind of step through the process here quickly. So once you have it set to implicit nonlinear, the first thing you probably would do after you have your model created is define materials. So go to the materials application, and under here you'll see we support the standard isotropic, orthotropic, composite. And one thing that's different is that we now have hyperelastic here as the main menu, because hyperelastic is a primary Nastran material, so we want it to be up front in this list. So under each one of these things, you would define different constitutive models, be it linear elastic or nonlinear elastoplastic. So all of this input now is specific to setting up particular cards in Nastran. For instance, linear elastic would be your MAT 1 or your MAT 2, MAT 3, your MAT ORT, or your MAT 9 cards, depending on whether you're doing isotropic, orthotropic, or isotropic, anisotropic. Nonlinear elastic allows you to set up a MAT S1 entry that's elastic, so it's like a piecewise linear elastic, nonlinear elastic material. And then elastoplastic is your MAT EP card in Nastran. Of course, you can't have a MAT S1 and a MAT EP in the same card, but you can set up the constitutive models at the same time. If you try to use both of them at the same time, the code will alert you to that fact. And the failures are your MAT F cards. And if you set this to hyperelastic, this allows you to set up your MAT HE, hyperelastic materials. And if you set this to composite, then that allows you to set up your PComp or PComp G or PComp LS or PLComp cards, depending on what type of elements you'll be using. Okay, then moving on to properties, you go to the properties tab here, and here you can set up all your different 0D, 1D, 2D, or 3D properties. So for instance, 2Ds, you have your shells, bending, membrane, shear panels. 2D solid elements allow you to set up plane strain, plane stress, or axisymmetric, and 3D allows you to set up solid elements. They can be homogeneous laminate, gasket elements. So all of these are specific to Sol 400 now. And one thing I would like to point out when you're setting up element properties is when you go to the properties form, you'll likely will see a nonlinear formulation when you're doing standard formulation. If it's not a standard formulation, it's going to set up your properties so that it will write out the property extensions. So if you're familiar with Sol 400, you know that you write out something like a P solid, but if you want it to be a nonlinear, also you have to write out an extension card, which is say a P solid N1 card in this case for 3D. If you do a standard formulation, we give you the option of determining this automatically or setting it to large strain or small strain. And what that does, if you set it to large strain, it will force the writing of the property extension card. If you set it to small strain, then it will force it not to write that, and basically reverting your element back to a small strain formulation. If you set it to automatic, then it's going to determine whether it needs to or not by what you have defined in your analysis. So if you have elastic plastic materials or you have contact defined and you have it set it to automatic, it's going to determine whether it needs to write out that property extension or not. Okay, and then moving on to the next item that you would define, say, setting up your analysis would be your loads and boundary conditions. Here we have combined all of the structural and the thermal loads. So you'll see your structural loads on top and you'll see your thermal loads down on the bottom, and contact is also defined here. So these are all within the same preference, whereas in the structural preference you would only see the structural loads, and setting it to the thermal preference, then you would only see the thermal loads. So this is allowing us to then be able to do coupled analysis, whereas before you couldn't do it if you were just in the structural thermal preference. One of the big items here is contact. So contact allows you to define your contact bodies, whether they be deformable or rigid. And then in addition, you can set up contact body pairs. And the contact body pair is where you define which contact bodies come in contact with other contact bodies. There are two different methods of defining your contact interaction within Patran. The default is to use contact body pairs, but we also still support the old method, which is defining a contact table. And I'm going to go show that to you in a minute when we get to the analysis form. The difference between the two is that contact body pairs, when you define a contact body pair saying that this contact body contacts that one, you're setting up something that is stored within the Patran database as an actual entity. So a contact body pair is an actual entity that you define in the database. So for instance, if I were to show you here a plot marker. So let me show you a contact body that we have set up. So if I plot this body, you'll see that that middle pipe there is a deformable body, and this one is a rigid body. So you can see this is highlighted. This one will show you the outer surface, outward pointing surface of that contact rigid body, and here's the upper one. So these two items, these two rigid bodies here that I've just plotted, they're going to crush this pipe as they move towards each other, which is this contact body. Now, we've also defined contact body pairs. So this is saying that the top will contact the middle one, and you can see that it's drawn an arrow from the middle deformable body to this rigid body. And this one is also the contact pair for the upper rigid body contacting the pipe. So those are actual contact body pairs that are entities in the database. So you define your materials. I might go back to materials also and mention something that Ted also mentioned was here, that we have also, if you go to linear elastic, you'll see that the structural materials and the heat transfer materials are all defined in the same place, again, allowing us to set up coupled analysis. So you define your materials, you define your properties, you define your loads, your boundary conditions, your contact bodies, and then you set up your analysis by going to the analysis preference or tab. And here you see we have two jobs set up. I've got one just called Crush, and then the one called Crush 400 modes. This one is an illustration of just doing the default. So when you go to the analysis form and your type is set to implicit nonlinear, you can simply just press the apply button here, and it will take all the defaults. The default is to run a nonlinear elastic analysis using a fixed increment scheme. It will use contact body pairs if they're in there, and it will use a default load step. So if I bring this up, you'll see that it has one subcase with a default load step. And you don't need to do anything. You just need to press the apply button and it'll run the analysis. Now I have another job in here to show you the versatility here. So in this case, I'm actually doing a perturbation analysis where I'm going to define two subcases. The first subcase is doing a modal analysis where I've actually set up a step for calculating modes, which I'll show you in a minute. And then the second subcase is going to do a default nonlinear static analysis followed by another modal analysis, which will calculate the modes based on the deformed shape, your final state of your nonlinear analysis. So I actually have two steps here. I have this default step, which is an available load step that I've set up, and I have another one called modes. And it's fairly simple to come in here and set up subcases and steps. You just simply come in here and click on your job up here and you say add subcase, and that'll add a subcase. And then once you have a subcase under here, you right mouse click on it and you add any load steps to that subcase that are available to you. SOL 400 does have some limitations in which type of load step can follow which type of load step, or how many you can have, or whether you can have a heat transfer followed by a linear, a static analysis, or what. This is fairly smart in that when you try to submit the analysis, if you set up some load steps that are incompatible, it will tell you, and then you can come in here and you can fix it. You can add load steps through this menu here, or you can simply come over here and highlight your subcase and then come over here and pick an available load step and it'll add it to it. You can come over here and you can remove the load step. That's how simple it is to set up your load steps. Load steps are actually set up under the load steps analysis form. You click on this and this allows you to create your load steps. So I have a default load step and I have a modes load step. You'll see the default load step is a static analysis. The modes load step is a normal modes. And these are the different load steps you can set up right now: statics, normal modes, buckling, transient dynamic, steady state heat, and transient heat. Each one of these, when you set one, so if we go back to this one, each one has their own set of parameters. For instance, a static load step, you set various parameters, whether it's a linear load step or nonlinear. The load incrementation, the load iteration parameters, these are all items that get written out onto the NLSTEP card. For instance, fixed analysis stepping, adaptive analysis stepping, your iteration parameters for conversion criteria. These are all set up under your load step. And for modes, then you have different ones also. So here we have the eigenvalue extraction method that can be set. And each one of the different analysis types has different parameters that you set up. The output requests are also part of your load steps. So in this case, for our default nonlinear static step, we're requesting displacement stresses and nonlinear stress and contact output. Okay, all of this stuff is created under a load step. And then you select your load steps that you want active for your particular analysis under this form here. There are other forms on here like translation parameters. These are job specific. Typically, all the defaults are usually what is set for you. You usually don't have to come in here and set any of this stuff, but if you do need to set certain translation parameters, you can set them there. Also, particular solution parameters can be set. Again, the defaults are usually what is needed for most analysis. One thing I do need to point out here, as I mentioned earlier, there's two different methods of defining your contact interaction. That is set under the contact parameters form. So under contact parameters, you have the ability to say, do I want to use a contact table or do I not want to use it? If you, by default, this is off. So if this contact table is off, then you are going to use contact body pairs. If you turn this on, then you're going to be using an actual contact table. So for instance, I've turned this one on, okay? And then I go to my load steps, and for my static load step, I'll come under here. You'll see now I have a contact table button. Now I can define my contact interaction through a contact table. Basically is a matrix showing all the available contact bodies here and across the top and the columns. And then you click on a cell to say whether you want it to be a touching contact, or toggle it to be glued, or no contact at all, or back to touching. And you can set all the parameters for each contact interaction. Each cell is basically a contact body pair. So this is saying contact body. This is saying that contact body 1 contacts contact body 2, and then anything you set here, under here with this cell highlighted, are the properties for that contact body pair. Okay, well, I'm running out of time, so let me go back to my job here. I just want to show you what happens when you actually press apply. You can press apply and you can run this job. Okay, and it will then submit the job to Nastran, and while it's running, you can come under here and go under monitor, press apply, and a form comes up showing you the increments that it's on and that it's actually running, and some other parameters, how many cycles it's gone through, an accumulated and per increment, and then when the job is done, it'll give you its exit status down here, which should be coming up pretty quickly here. We'll let that run. Okay, and successful completion. Let me just show you one other thing here. There is a tool under modeling for contact bodies. And let me open another database here. Okay, here's a more complicated model with a bunch of contact bodies. Actually, the bodies haven't been created yet. There is a tool under modeling contact bodies which allows you to automatically create your bodies. So let's say I want to create all my deformable bodies and they're 2D. I can just press apply. I'm going to create them based on connectivity, 2D elements over the entire model, and I press apply, and it automatically creates all my contact bodies for me. I can go under loads and boundary conditions, and I can show you that it's actually created those. We'll put up a plot of deformable contact bodies, and we'll just color code them so you can see that. Okay, so there's the color coding of all the contact bodies it actually created. And you can also automatically create your contact body pairs. So let's go under here, and let's say you can select a few bodies here. So let's say you want to do all those bodies less those two bodies, and there are properties that you can give your bodies, which I don't have time to show you, but you can define those under properties, and you would pick them here, and then you just press apply, and it automatically goes and creates your contact body pairs. Then you can come back and take a look at those. Let's say we want to look at contact body pairs. So let's take a look at, say, that one, and press apply, and it shows you that this contact body can come in contact with that one, and you see the little arrow there. Okay, and one last thing I do want to mention before I finish my demo is what happens when you import a model. So let me close this database and open a new one. Actually, I'm just going to open a new database. Okay, I'm opening a new empty database, and I'm going to import a job. All right, so when you open a new database, the default is the structural preference. So if I read in a job that's a Sol 400 job, so I'm going to say read input file. I'm going to select the input file, and here's the job we ran, Crest 400. You'll notice that the structural preference is set, and if I press apply, it's going to detect that this is a Sol 400 job. It's going to say Sol 400 deck is being imported. The analysis preference is not set to the implicit nonlinear. Would you like the preference to be changed to implicit nonlinear? And if you say yes, then it will change the preference to implicit nonlinear, and you're good to go. If you say no, which is what I'm going to do, then it will import it as a structural preference. Now, you can still run Sol 400 from the structural preference, so this is okay. And then you can change the preference to implicit nonlinear, and it will switch everything over to the implicit nonlinear preference, and you're good to go, and you can run the job. Now, there are some incompatibilities between the structural preference and the implicit nonlinear preference for certain material properties, for certain element properties. If it detects those, when you go to the implicit nonlinear preference, it will let you know, and it will ask you whether you wish to convert them to be compatible. And those that can be converted will be converted. And those that aren't, if you say yes, it will convert them. If you say no, it will not convert them, and it will still allow you to work in the implicit nonlinear preference, but those things that can't be converted will not be translated into your Sol 400 deck. And at this point, I'm going to stop sharing and send this back to Ted and Srinivas.